Today we're reviewing inference for means covered in chapters 23 through 25 in Bach-Velleman-DeVoe. Well, all the inference procedures for proportions were based on the idea that if certain conditions were met, you could use a normal model to represent the sampling distribution of a proportion. What we learned in chapter 23 is that unless the standard deviation of a population is known, a normal model is not appropriate for inference about means. Instead, the appropriate model is called a t-distribution. Now, t-distributions look a lot like normal models. They're unimodal and they're symmetric, but they're fatter in the tails. So the smaller the sample size, the fatter the tail. Now, in the limit as n goes to infinity, the t-distribution becomes normal. So as we get a bigger and bigger sample size, those fat tails become skinnier and skinnier and skinnier until the t-distribution is the same as the normal model. Degrees of freedom, which for t-distributions for means is n minus 1, are used to specify which t-model you're using because there's a different one for every sample size. Now, the t-table in the back of the book or that you would be provided with for your test, it only has t-scores for certain degrees of freedom and the most commonly used confidence levels or alpha levels. So if using the table and desired value is not shown, then tell what it would be between or err on the side of caution and choose the more conservative degrees of freedom or the more conservative T star or whatever, which is usually the one above on the table, the one higher. Use technology to avoid the pitfalls of the table when possible. Okay, how do you calculate a confidence interval for one mean? Well, you start at the sample mean, x bar, and then you're going to add and subtract a t star times the standard error. So t star will depend on your confidence level and degrees of freedom, which we'll talk about in a minute. And then your standard error is the standard error we learned in chapter 18 for the sampling distribution for means, which is sigma over the square root of n, but we're estimating sigma with the standard deviation from our sample, s sub x. Okay. Remember that the margin of error is this whole thing here that you're adding and subtracting, and it tells you how many standard errors you're reaching out from the statistic. In your calculator, to create a confidence interval for one mean, the test is called t-interval. Okay. Finding the critical value, that t star, how do you do it? Well, draw or imagine a normal model with C% shaded, symmetric about the center, so like 95% shaded. What percent's left in the two tails? What percentile is the upper or lower fence at? Look up that percentile in the t-table to read off t, or use inverse t, 0.95, comma the degrees of freedom, or whatever percent is appropriate if it's not 0.95. Okay, so it's the same way we found z star with the exception that you use inverse t instead of inverse norm, and because it's t you have to specify the degrees of freedom, and when you're using the table you may not find the exact t, so again you may have to go one up in the table. Okay, finding sample size, the same way we talked about with proportions, you might be asked for means. They might say, I want this margin of error and I want this level of confidence, what sample size do I need? So remember that margin of error is your critical value times the standard error. So t star times the standard of error. Plug in the desired ME, like I want to know within 5 inches, right? So our margin of error might be 5. And then plug in the z star for your desired level of confidence. Now guess what? We can't use t star because we don't know the degrees of freedom, because we don't know the sample size yet. That's what we're trying to find. So it's actually a little bit easier because you get to use z star instead of t star. No way to figure out t star. Okay, plug in the standard deviation from a sample or a believed true value and solve the equation for n. Okay, so again, if you look in your textbook, there are some examples of that there. Conditions that we need to check when you're doing inference for means. We need to check for random, just the same thing that we did, just the same as we had to for proportions. 10%, okay. Independence, all those are the same. And check if data are paired if you have two lists. There's no NP and NQ to check here because we don't have a P or a Q, right? So we don't have a success-fail condition or anything like that. How do we do a hypothesis test for a mean? Well, you state your hypotheses, right? H sub naught mu equals whatever we're hypothesizing it is. Remember, we're using Greek letter parameter for mean. The alternate would be H sub A colon mu equals is greater, does not equal, is greater than, or is less than whatever you hypothesized. Okay. Um, Remember again to use your Greek letters there, and don't forget to write that. Sometimes people will write down H naught equals 5, and they forgot to write mu or p or whatever, so be careful about that. Then your hypothesized model, right? If you draw the model in question, it would center at the hypothesized mean, and it would have a standard deviation of the standard deviation of your sample over the square root of n. And then you would find the value that you got in your sample on that model, flag it, and then you would look for the test statistic, the t-score, analogous to a z-score, of that sample value or more extreme, using n-1 for the degrees of freedom. Use a table to do that, or you can use TCDF in the calculator. And so TCDF, you would put in the lower bound of the shaded region, comma, the upper bound of the shaded region, comma, the degrees of freedom. Don't forget to double it if you're doing a two-tailed test, otherwise you only have half of the p-value. Now on the calculator, it's called the t-test, and you would report the t-statistic, the degrees of freedom, and the p-value. Now if you have two means instead of one, you need to find out if your data are paired. Okay, so if they are, you would subtract the higher list minus the lower list to create a new list, and then do the exact same thing you did before. Just do t-test or t-interval. And by paired, we mean that you could not, say, reorder the data in one of the lists and have it still make sense, right? Basically, this value, the first value in this table, has to go with the first value in this table because of the situation. If data are not paired, okay, then you're not doing a paired t-test or a paired t-interval. You're comparing two means, like from two completely different groups, and trying to decide if they're the same or different. So you would need to check nearly normal for both groups. Both must individually be over 30, or you have to sketch each group's histogram and say that they could have come from a normal population, right? Yeah, I think I forgot to mention that here. I accidentally skipped over the nearly normal condition. Nearly normal condition is that sample size is greater than 30, so that the distribution has a chance to get normal-ish, right? Or you could sketch a histogram and say that the sample could have come from a normal population. We're not checking if the sample itself is normal, we're checking if it could have come from a normal population. So be sure to state that. Okay, so when you check nearly normal, check it for both groups. Label the two histograms so you can tell which one's which, so they know you actually checked both. Or say that both samples are over 30. Your confidence interval would be the difference in the means plus or minus the margin of error. Use the calculator to do this because finding the degrees of freedom and therefore also t-star is rather complicated. So it's extremely unlikely that you would ever be asked to do this by hand. You can use the calculator for a confidence interval for the difference of two means that are not paired. The standard error for unpaired means is the square root of s1 squared over n plus s2 squared over n2. And if the calculator asks pooled, always choose no for these kind of procedures. And your null for paired is usually that the mean difference is 0, but your null, if the data are not paired, is usually written as the mean of the first group minus the mean of the second group equals 0. But don't forget to define those variables. Don't just say mu1 and never say what mu1 is, right? Make sure you say that this is the mean of the women, this is the mean of the men, and be as specific as you need to be. So like maybe this is the mean weight of US women, this is the mean weight of US men. So don't forget to define those variables and make it clear when you define them that you're talking about the parameters, not the statistics. You're talking about the population, not the sample. Then you use a two-sample t-test or a two-sample t-interval, depending on whether you want an interval or a test, in the calculator for data that are not paired. Okay. In general, what do you need to write down whenever you do a hypothesis test? So we used the process state, plan, do, conclude. So start out by stating, name the test or name the interval. So like a t-test or a paired t-test or a two-proportion z-interval. Write your hypotheses. If it's a test, state your alpha level, okay, and define your variables. Okay. The plan is checking all of your conditions. Check marks and yes is not good enough. You need to say a little bit or show a little bit of math to verify that you actually did check them and know what you're doing and that You just didn't have a list memorized and put check marks on them, but don't know actually how to check them. Okay. The do is the interval that you get if you're constructing an interval. If you're doing a hypothesis test, you would state your test statistic, the degrees of freedom if appropriate, and the p-value. It is good to write the sample difference if you're doing inference for two proportions or two means as well. But make sure that you don't have any undefined variables in what you write in the do. And then finally, your conclude, that's interpreting the confidence interval or the hypothesis test, which we learned how to do in previous review slides. Okay, so now let's take a moment and look at where all these things are in the calculator. I've got some data in some lists, I believe. Let's see what we've got. Yeah, so we have some data and some lists. Let's just go play with it for a minute. So if we go to stat test, that's where you find all of these. So yesterday we talked about one proportion z test. So that's, doing a hypothesis test about whether a proportion is or isn't something. There's two proportion z test if you're comparing two proportions. You scroll down, we have a one proportion z interval and two proportion z interval. Those are all of the tests and intervals that we use for proportions. Now for means, if we go back up, we had t-test. Be very careful not to accidentally go into z-test. Okay, t-test, okay, or t-interval if we only have one. Okay, those two right there. And then we also have the two-sample t-test and the two-sample t-intervals, which are up here somewhere. Gone too far. Okay, right here. Two-sample t-test, not z. Be very careful about that. And then down somewhere here is the two-sample t-interval. Be very careful again not to accidentally go into z. Okay, so when you go into these, it's going to ask you data or stats. And so data you would use if you have put the data into lists in your calculator, and then you would just tell it what list it's in. Stats you would choose if you don't have the data, but in the problem they told you stuff like the mean or the proportion or whatever you're going to need to type in. Now what are these asking for? This is asking for the mean of group 1, right? This is the standard deviation of group 1. This is the sample size of group 1, so on and so forth. And then we can scroll down here and see what else they ask for. Confidence level, pooled, remember the answer is always no, and then calculate. You might want to practice at least one of each of these just to refresh your memory about what are the different things that you have to put in, and just reminding yourself of what those things are. Okay, let's take a moment and look at a one proportion z test. Okay, so here it's asking for the hypothesized proportion, and then x is the number of successes you actually had, n is the sample size, and then the direction of your alternate, and then you can calculate, right? So let's say I have a hypothesized proportion of 0.4. In my sample, I actually had 125 successes out of 300 trials, and I want to do a two-tailed test and then calculate, so on and so forth. And so here I have, this is my z-score, my test statistic, and my p-value. I would probably not report these guys. Okay, this is the actual p-hat from my sample right here, 0.41667. That's the 125 divided by 300. I have a p-value of 0.55. That's way above alpha, so I would be failing to reject the null there. Okay. So again, all of these things are here. Now, if you're looking for, calculating a test statistic like a t-star or something, then those are located under the distribution menu under the vars key. So here's normal CDF, which is used for finding area under a normal model. Inverse norm, which is used for, you put in a percentile and it gives you the z-score. Inverse t, which you put in a percentile and it gives you a t-score for specified degrees of freedom. And then TCDF, which gives you the area under a t-model. Okay, so again, practice using all of these with different problems so that you know what it's asking you to input, and you're just familiar with all of them before you go and take the exam.